We are live on YouTube now.
Porque no escucho nada.
Karina.
Sí, profesor.
¿Me veo acá?
Sí, ahí se ve.
Ya. Yo también, ¿cierto?
También el profesor Kaneshiro.
Ya. Bueno, vamos a comenzar entonces. Bueno, hoy tenemos la presentación de Ingeniería de túneles en países susceptibles a grandes sismos. Y la presentación se enfocará en los fundamentos de la vulnerabilidad sísmica de estructuras subterráneas, incluyendo algunos casos históricos y el comportamiento, la respuesta que han tenido. Nuestro invitado de hoy es Jon Kaneshiro, Bachiller en Geología y Máster en Ciencias de la Ingeniería en la Universidad de California, en Berkeley, ¿ya? Tiene una amplia experiencia de 40 años en diseño y construcción de túneles. Como está anunciado, la charla va a ser en inglés, ¿ya? Y al final de ella pueden hacer preguntas, las pueden hacer directamente en inglés, o si las hacen en español, las traducimos acá. Así que, muchas gracias, Jon. Puedes comenzar.
Okay. Muchas gracias, profesor. Buenas tardes. Muchas gracias. Good evening. Thank you very much for this opportunity here at the University of Chile. I thank you for the opportunity to present on approaches to seismic design of tunnels. Just a side note, this talk was originally scheduled for October of 2019, but there was social unrest at the time. And then in April of 2020, and we had COVID. It was arranged with Professor Edgardo, with Francisco Medina, who I met in 1990. And we've kept in touch. His genuine friendship is appreciated very much. His willingness and desire to share his country and the opportunity to present to you all is very much appreciated. The presentation will focus on the fundamentals of the seismic vulnerability of underground structures, including some case histories and their seismic response behavior due to shaking, as well as to large displacements. Examples of design strategies used for new designs and retrofitting designs or repair will be presented. Here's an outline of the presentation. About half of my slides are reviewing the simplified approaches to the fundamentals of seismic design of tunnels, and a bit about its evolution and the empirical databases. Then I will share the inherent ductility of tunnel design, of modern tunnel design for shaking, and the details for designing for larger offsets, for faults, for example. And then I'll present some illuminating case histories. At the end, I'll provide you with a list of references for those who want to dig deeper, delve deeper into these topics. This presentation wouldn't be complete without showing the ring of fire in all the countries that are susceptible to major earthquakes, those due to strike slip and the thrust environment and normal faulting. And I just thought we should at least include this. So this first topic, with respect to ground motion and seismic waves, there are 4 fundamental waves, the body waves that travel within the surface of the ground, which are the primary compression, the pulse, the one you feel first, and then the secondary wave that comes later, which includes the shear and the transverse waves. Right here. And then the above ground waves on the surface includes the Rayleigh waves and the Love waves. These wave effects on tunnels are shown diagrammatically by these figures for compression, bending, and hoop deformation, and for rectangular structures for racking. In general, tunnel liners are like an embedded piece of cooked or uncooked piece of spaghetti noodle in a medium that may range from flexible material like jello or gelatin to stiff material like a brownie. The liner can be flexible relative to the ground, in which case it tends to move with the ground, or what we call move with the far field strains. The term aseismic, I guess, has been around for over 100 years, but I saw it more frequently in the 1980s, meaning without seismic or inherently resistant to seismic destruction. So that there is some benefits to have things below ground as opposed to a tall building. In general, for earthquake shaking, if one designs a tunnel for static conditions, inherently there's a typically enough reserve in the liner that for shaking, at least, it is safe due to shaking. This is a little bit of the development of the design of seismic strains in the United States, and for seismic strains and liner stresses, looking at simplified closed form solutions, analytical solutions, as opposed to numerical models. And it assumes that the ground moves with the liner, and then many investigators, the references are provided at the end, provide various stiffness factors or stress concentration factors using formulas or charts to simulate the ground structure interaction. Here's the closed form strains are given by the following equations, where VP, VS, and VR is the compressional shear wave velocity, Rayleigh wave velocity, and of the medium. I'm sorry. VP, VS are the Rayleigh waves measured by the earthquake, respectively, and then the C. P, C sub S, and C sub R, the apparent horizontal P wave, S wave, and Rayleigh wave velocities of the medium, respectively. And phi is the angle of incidence to the tunnel, and it would be these numbers here is where the value of the strain would be at a maximum. In some cases, it's at incident angle of 0 degrees, 90 degrees, 45 degrees, or in some cases about 35 degrees. And you add these strains together to get the composite strain with the plus or minus the curvature strain. Again, it should be noted that these can be modified by the various investigators and the references given using dynamic stress concentration factors and the various charts they have provided. For simplified analyses, the Multidisciplinary Center for Earthquake Engineering Research and the Federal Highway Administration published guidelines for obtaining the PGA when you get it from the preliminary screening. You get the site acceleration, and then you can use these simplified methods as tunnels are deep to as much as 30% less acceleration from the ground surface acceleration. This was done by C.Y. Chang and others in 1986 for the Nuclear Regulatory Commission, and it was adopted by the tunnel industry. Also, these factors were used to characterize example site for rock, stiff soils, and soft soils, and for source to distance from the hypocenter, epicenter to your location to various magnitude earthquakes to get your V over A relationship. And then once you get the A, you can calculate the V and therefore the strains. This was adopted from Ross Sadiq and John Egan. And it's become a standard in the industry in the United States for simplified analyses. The next step is to determine the apparent horizontal wave propagation velocity, which for me has been a pet peeve since I started working on tunnels as a junior engineer. And it's the velocity of a traveling wave from the source region to the tunnel site, as shown by this diagram adopted from Owens and Scholl. There are a number of different paths that the direct body waves can take. This is the most direct, which is what we most often feel when we experience an earthquake. But they can also be reflected and refracted waves, which are a bit slower. Well, in some cases, they can be faster depending on the condition. It depends on how deep the earthquake is, the layering of the overlying ground, and the material where the earthquake focus is. The one we can measure without much effort is the direct body wave path, as we discussed and shown on the next slide. So the first wave we feel is a P wave. Many of you have gone through this scenario. I experienced it in the 1989 Loma Prieta earthquake in San Francisco. I was in Palo Alto and my colleague was in San Francisco, and we were discussing a tunnel project. And this is precisely what happened. I felt the earthquake, my furniture and books started falling on me, and he felt nothing until about 15 seconds later, and then click, the phone went off. And that was the apparent horizontal wave velocity, about 4 kilometers per second in that case. This is, to me, it's a quite complicated topic. And the industry has generally been conservative. And what they have done is to use the apparent horizontal wave propagation velocity from geophysical tests. There have been attempts to correlate, for example, what we measure from geophysical tests from seismic reflection or seismic refraction by this equation. And it depends on the angle of incidence, but the angle of incidence in radians between 0.5 to 0.20 degrees calculates to about 0.35 to 15 kilometers per second if we use O'Rourke and Wang's equation. But basically the observed range is about 1.5 to 10 kilometers per second. So it goes in the denominator to calculate the strain. So it's very, actually gives you very low strains. And typically we have an average of about 2 to 5 kilometers per second in most earthquakes. But in practice today in all the manuals that I cited in the beginning in the evolution, and starting with LA Metro was one of the first, they use the, for the apparent horizontal wave propagation velocity, which is quite low. And so it leads to in the denominator, it leads to very high strains, but it's conservative. And that's the reason why they've chosen it. But I don't believe it causes any over design of the tunnels because of the already aseismic behavior of modern tunnel construction. I think the best discussion is in the Owens and Scholl publication, and you can download that for free on the internet. That's one of the, and also Joe Wang publication when he was at Parsons Brinkerhoff has a nice discussion of C, the apparent horizontal wave propagation velocity, and its limitations. Okay, now I'm going to delve a little bit into just some empirical correlations about the damage, and this is kind of the history. I didn't bring my references with me. I left my external hard drive at home, so I couldn't find all the numbers, but various investigators at different times looked at case histories to look at damage of tunnels from various earthquakes. But the first widely cited investigation was by Chuck Dowding and Rosen at MIT. And they looked at 71 cases, 7 earthquakes in the US and 6 in Japan. And most of the cases were in rock and unfractured rock, and only 3 cases were in tunnels. And then Owens and Scholl updated to 127 cases, but they didn't provide a plot. And then Sharma and Judd, which I'll present in a little bit later, categorized it into different types of liners and so forth. And then the study I was involved for, the MCER and FHWA, we basically corrected the attenuation relationships. So we used the latest attenuation relationships at that time to correct the previous data by Dowding and Rosen and others. And then I'll just share this last one by Andy Kozitsky and Scott Lewis, who updated the database to include wine caves in the Northern California Napa region. So here's the Dowding-Rosen one on the left. And basically slight damage between 0.2 and 0.5 and more damage above 0.5 and 0.6, and then no damage below 0.2. So we, in 1998, as I said, we updated the attenuation relationships. We categorized it like Sharma and Judd into unlined tunnels, timber or masonry tunnels, older tunnels, unreinforced concrete liners, and reinforced concrete liners. And that included shotcrete liners. And we basically came up with very similar results: slight, moderate, and heavy damage. No damage is the circles, slight damage is the squares, moderate damage is the triangles, and heavy damage is the diamonds. Now, superimposed on this is the study by Kozitsky and Lewis, and they had an earthquake in 2014. There's hundreds of wine caves up there. And so they had a lot of information, a combination of accelerometers and the USGS map of the accelerations in that area. And they plotted these dark, and they're all basically 90% of them are no damage and then some very slight damage. And they added about 31 case histories. And then here's Sharma and Judd. They provided useful charts. It's often cited. You can see where the tunnel lies within the susceptibility to damage. They correlated, as we discussed, seismic vulnerability of tunnels up to 6 parameters: tunnel cover, which tended to be a very important one, subsoil type, peak ground accelerations, and magnitude of the earthquake, distance to the epicenter, and type of lining support. But most of the damage, 60%, were affected by shallow tunnels, depths less than 60 meters, less than 100 meters. And many cases, 40%, 42% concerned unlined tunnels and rock. This is an area of further research that it could be a PhD or master's thing where they could actually update this database. I think it's quite useful as an empirical method to the beginning screening process for evaluating your planned tunnel. Now I'm going to briefly just show a few examples of ductilities in tunnel design inherent. This so-called aseismic behavior, particularly even in rock tunnels nowadays, we're using segmented tunnels for groundwater inflow or other reasons, but it's naturally articulated. As you can see, it has all these joints. And then they typically have ductile fastening pieces. And then typically there's caulking grooves and relief. So you won't chip the segments during handling. There's gaps. And there's also many contractors prefer to use packing, fiberboard, marine packing, so that when they put the jack forces on the TBM and push the segment behind them, it also provides for damping. And then in special cases where you need it, they often actually have grommets here for water leakage. But Professor Ono in Kyoto, the late Professor Ono, proposed this at the Earthquake Engineering Conference, and now you can get these off the shelf in Japan, neoprene washers that they make specially for this to increase the ductility when you need it for larger movements. This is a fault crossing, but it's for a very small amount of faults. This is diffuse end of the San Andreas Fault way down in San Diego, where we have what we call step apart, pull apart basins and the right stepping, and the movement becomes less and less. And down here, we did a probabilistic seismic displacement analysis. And we came up with about 3 inches, 7.5 centimeters for the 975-year return period. Now, why did we have such a high return period design criteria? For a metro, it makes sense to have a high return period, but for our case, we only had advanced primary effluent. So that's why we had it. And it was so diffuse, we decided we could design for such a small movement. And what we did is we learned from the Taiwan metro, and we put in ductile steel bars, number 11s or number 10s, connecting the segments. This is a planned view of the segment. And then we coupled them. And the primary reason for this is just to keep the gaskets closed. The problem with this, though, is in hindsight, we should have put neoprene in here. It's a flexible thing, because when you do a detailed finite element analysis, you'll find little chipping and spalling here, which is not good. And basically, we design this by looking at the seismic reflection data from what the fault width is, and there's an uncertainty associated with that we get from the geologists and geophysicists. And then from that, we get we do a beams on an inelastic type foundation analysis or a flak analysis, and we get the total affected length and then the uncertainty related to that. So in this particular example for San Diego, it averaged about 150 feet, 40 to 50 meters. And we had 13 faults, but they were very small amount of displacements. Now I'm going to talk about introducing ductility for larger faults, for example, landslides, which you normally don't put in a tunnel through landslides, but if you had to. So for a cast in place liner, you can segment your reinforced cast in place concrete liner by putting marine packing board, just like you would for a segmented liner, and you can put in water stops, and you can put in sliding sleeves to account for any separation that might occur from the P wave, for example, or from the S wave from snaking. Another example, this is for a 2-pass liner with a pipe inside a tunnel, is you can, and this has been done on numerous projects, even before this, is on the, let's say on the reinforced concrete pipe design or the steel pipe design, you introduce a longer joint to accommodate the movements. And you often have double gaskets, even without seismic, even static conditions, they use double gaskets. Another method is for transportation tunnels, they enlarge the tunnel. This was done on the Gold Line. So after the fault moves, they actually put steel liners on the subway here, and then they went to concrete, but they actually enlarged the cavern. So if the fault occurs in its lifetime, you can realign the tracks within the liner. You put in an S curve. And this was also done, we'll get to another case history. And then for water tunnels, this is often a strategy, either without packing, they put it sometime on Teflon, or they put in frangible backfill. And this was done on these example projects here, and one under construction right now for a 6-meter ID tunnel with about a slightly smaller steel pipeline but in many cases they actually put it on Teflon pads, or they just leave it in air and then reposition it later, which was done on this example for the other projects. Okay, and then we get into the finite detailed numerical modeling. This figure on figure A here shows we modeled it without any connecting dowels, and you get a discrete displacement at one location. Then we put in the plastic dowels, and you get some damage here. And then we put in steel, you get more damage. So you need ductile pieces to cushion it from, the rebar connecting it. And then this case here is with a backfilled steel pipeline. This is for 1 foot of displacement. No, 20 inches of displacement, I'm sorry, for a 1 foot wide fault zone. There are closed form solutions for this as well. They're very primitive, but these are used by the oil and gas industry and the water industry, and by Newmark and Hall, as well as Kennedy and others. And then this is the most elaborate example for segmented tunnel liners for a fault crossing for the metro in Greece, where the joints were fastened and made more articulate or ductile by introducing a combination of embedded bearing plates and springs to accommodate movements, and neoprene washers and other locations where the movement wasn't quite right. So this is also used on the project in Greece. And there's projects in California now under design, the BART tunnels, that it will be the larger than the Alaskan Way Viaduct, over 15 meters, and they they will need detailing like this for, not for shaking, but for, actually, if it wasn't for water, you don't even need bolts because the compression and the grouting afterwards locks everything in afterwards. Now I'm just going to focus on a few illuminating case histories. Of particular interest to you will be case histories 2, 3, and 4. Engineer told me about the Francisco told me about the San Ramon fault here in Santiago, and which has a thrust component, vertical component. And these case histories 2, 3, and 4 will be interest of you, even though this case history in Turkey is a strike slip environment. The movement associated with the damage they had was suspected to be on fleisch deposits on weak plains, vertical, subvertical plains. So this first project case history is kind of interesting. It was for the Hetch Hetchy Aqueduct that supplies drinking water to San Francisco. This is the outlet works to San Andreas Dam. San Andreas Dam is right here. This is the Crystal Springs Reservoir. San Francisco is up here to the north. And faulting occurred here, 8.3 foot across the fault, all the way down to Hollister. And the final shaft configuration was like this. And the gate well, originally located here, moved about 8.3 feet to the northwest. And then this outlet tunnel right here moved counterclockwise, clockwise, I'm sorry. And there was about also 4.6 feet of extension. Now, Andy Lawson, who's a Berkeley professor, did a report for the Carnegie Mellon report. And he stated in that report, the width of the zone of surface rupturing varied usually from a few feet to up to 15 meters or more. Not uncommonly, there were auxiliary cracks either branching from the main fault trace obliquely for a few hundred feet or yards or lying subparallel to it or not. So far as disturbance of the soil indicated directly connected with it, where these auxiliary cracks were features of the fault trace, the zone of surface disturbance, which included them at a width of several hundred feet. The displacement appears thus not always to have been confined to a single line of rupture, but to have been distributed over a zone of varying width. Generally, however, the greater part of the dislocation within the zone was confined to the main line of rupture, usually marked by a narrow ridge of heat and sod. Now, some investigators use that quote by Andy Lawson to mean that for geophysicists and seismotectonic investigators, they love that because then they make the problem bigger, I think. But I think that that's a wrong interpretation of Lawson and a wrong interpretation of what happened here. The trenching in this area by the USGS has shown in many all locations, it's confined to just about 1 foot. And I think this is borne out also in the recent earthquake they had in Turkey. And but people still believe it's can be widespread. But in this case here, it's certainly due to soil action of it's a 6-course brick sewer. It's only 6 feet by 4 feet. It's an oval tunnel. So many people It's happening on BART right now. They want to trench in the middle of the city, and LA Metro, same way, they trench and do studies. And who knows how accurate it can be in the interpretation. And the same could be due with the San Ramon Fault. The geologists decide to trench it, but it's very challenging to find the main trace, or if it's sympathetic movement and so forth. This next case history was the biggest earthquake in California since 1906, and with a modified Mercalli index at the site of greater than 11. And it occurred in the high desert of Southern California. Shaking was associated with a reverse fault. That's a dip less than a greater than 45 degrees with it had a small left lateral component. Tunnels 3, 4, 5, and 6 all got damaged. This is the fault zone right here, the fracturing zone, the surface expression. The tunnels were originally lined with timber sets, but then in many years later in the 20s, they lined it with concrete about 50 centimeters, 30 to 50 centimeters thick. Tunnels 3 and 4 here blown up were the most damaged. The concrete walls cracked, twisted, and collapsed, and that was in tunnel 3. And the distance between the portal here and the portal not shown off to the west there shortened by 2.4 meters and a 91 meter tunnel length. So there was a compression that occurred there. And then this number 4 was a very shallow tunnel, and the tunnel walls were cracked and broken, spalled off, and it had very low cover, and the walls buckled inward. And in some places, when they did the cast in place concrete, they did not anchor it to the floor. And so the rail tunnels slid under the walls in places they found. So in general, the extensive damage here was a combination of the low cover, probably the weak sheared material, which would be the case in an environment like the Andes. And also the number one contributor may have been that in the next case history I'll show is that the liner was not properly backfilled as you would today, grout the voids. This next case is in a strike slip environment. It was the Bolu tunnel. It connects Ankara with Istanbul. During construction in '99, there were 2 earthquakes. One was the Coachella earthquake in the fall or maybe summer, which they didn't have any damage to the tunnel. But then in November of '99, a bigger earthquake happened closer to the site, which caused deposits. There were 2 twin tunnels with these dimensions shown here for the roadway. And it was excavated through flysch deposits using NATM. And they were about 300 meters in. And they were in particularly soft clay gouge area. And they had pilot tunnels to build it. This is basically the footing for the liner. And I recall it was about maybe 12 feet diameter, 4 meters, maybe it was 5 meters. It looks like a classic hoop deformation. You had buckling of the steel liner, and most of the place it was just shotcrete and rock bolts, but where there was steel, it buckled, and the shotcrete liner buckled. And there's several speculation that it was just due to strong ground motion, which could be the case here, and if you were tunneling through the San Ramon fault. or possibly a landslide. I know they have landslide issues near the portal today. So here's the drives, and with only 300 meters in, they completely collapsed. So this is after they excavated it out, and this is what they found. It's just a beautiful picture of hoof deformation, actually. These other ones are of interest because this is a tectonic subduction zone like Chile. And it was presented by Shimizu and others. And it's all the presentation by Engineer Yashiro. And he shared his slides with me later. And it was due to what was called the mid-Niigata earthquake in a thrust zone environment. And it was for the bullet train, the Shinkansen. And there were 3 tunnels that experienced extensive damage because of the close epicenter, like the Bolu project and the current Southern Railroad, Pacific Railroad Tunnel project. And because these were not properly backfilled, there were voids behind the liners, and they had weak zones. So they attribute, so this is the Unuma tunnel. And then here is the Myokin tunnel and the Watanatsu tunnel. And they just basically had hoop deformations and spalling. And they attributed, and I'll show you on the next slide, to factors I will discuss. But one aside I want to note is that the Navy has a blasting design manual. It's thousands of pages long for the code for blasting design. And one of the graphs, which I have not shown here, but it shows rotation of concrete versus a damage. And at about 3 degrees rotation, you get extensive spalling and collapse. And you can use that method to, for example, on a segmented liner to interpret if you only have 0.3 or 1 degree spalling, you won't have collapse, it'll probably be okay. So this is the analogy. I think it's a handy graph, and actually it's provided in this publication here. Anyways, getting back to the presentation by the Japanese. Again, shallow depth was a factor, and poor geologic conditions, soft sediments, gouge zones, where you might have sympathetic movement, and poorly backfilled construction as we on the Southern Pacific Railroad. So, and this final one is unique to the Hayward Fault in the Bay Area of San Francisco. It's the effect of a creeping fault. The tunnel was built by J.F. Shea Associates for the BART project in 1965 to 1973 through sedimentary coastal range deposits. Weak rock, strong soil. And these are the twin bore road tunnels. They were constructed the old-fashioned way with ribs and lagging and backfill concrete. But it was designed for creep of 5 millimeters per year. They knew this happened because the Berkeley football stadium is undergoing creep, and they knew about that for years. So they oversized the tunnel. But the problem is it used up all its in 2019, they were at the point where they used up all the movement. These are the cracks at the side of the tunnel, and they needed to reballast the tracks and change it or enlarge the tunnel. So the fear would be that they would have to enlarge the tunnel and keep the BART running. So an ingenious, I don't know what the exact solution is geometrically, but the road and highway engineers and rail engineers, they are good at geometry and designing S-curves. So they were able to fit an S-curve in there, and they're going to realign the track. So you can imagine if they had to dig a larger tunnel still or move it, if you had to construct it in only 4 hours a day. So, but right now the strategy is to do it at night, because you have to prepare the shutdown. All the safety is 4 hours, and the actual construction time is only 3 to 4 hours. So, and that's to add added life to the art tunnels. So in conclusion, you know, a lot of modern tunneling techniques, and if you use the proper methods statically, it's inherently stable. And when you check it for seismic, it should be okay, unless it's for really large movements. But you can be creative and design ductile fastening members and that sort of thing. In general, in rock tunnels, the ground moves with the tunnel, and overall the tunnel performance and behavior has been pretty good for, 60% or more of the tunnels. And that's particularly true when the shaking is less than 6G. And again, this for fault crossings, it takes a lot of creativity and engineering and numerical modeling to understand what might be the best solution. Finally, I just would like to provide anybody who wants it. I'm going to provide Professor Gonzalez and all these PDFs, also with my notes, and these references coming up, which are categorized into empirical relationships, seismic design for shaking and large movement. My pet peeve, apparent horizontal wave propagation velocity, and fault crossing for tunnels and case histories. But I should point out that a lot of these publications overlap. So for instance, Joe Wang has a lot on closed form solutions and simplified methods, but he also has a detailed discussion on apparent horizontal wave propagation velocity, as does Owens and Scholl. And so here are the references. And if for some reason you can't find them, professor can reach out to me, and I'll be glad to send them.
Gracias, John. Si tienen consultas, por favor. Además, Karina, por favor, deja mi correo electrónico en el Zoom, en el chat, para que luego me puedan pedir la presentación que John nos va a compartir. Por ahora, si alguien tiene alguna consulta, la hace directamente, por favor.
Sí, quería consultar qué diferencia hay, o sea, o qué metodologías distintas hay para reforzar, digamos, una falla en roca y fallas en suelo, digamos, qué tipologías o qué instrumentación habría que aplicar para, digamos, más que nada para las fallas activas, ¿no? Prevenir, digamos, movimientos en las fallas activas, y por supuesto, mucho más si aparece un movimiento sísmico, ¿no?
He's asking what are the main methodologies to address issues in active faults, depending on whether you are in soil or rock. That's the question. And especially if there is a seismic event.
Just for
the movement to the
so
in case of moves.
What is the strategy for design or for planning the?
To address methodologies to address I think the question goes into the mitigation direction.
After it damage.
It might be to prevent.
To prevent the damage.
Oh, to prevent damage, you have to build in ductility, as in like neoprene washers, and or the extreme case where they had springs to accommodate it and gaskets to accommodate any water inflow. In some cases, the movements are so large that it's not inherently stable, so you have to go with other measures such as a steel pipeline inside. And sometimes in some sections it was proposed, though I have not seen it, to use cast iron segments to help with fault movements. Most of the time for the MCE event, you just only have, you accept the damage without collapse, and then you have to come in and repair it. Such as you oversize the liner, and then you can only fix it once by putting in a reinforced cast in place liner. That is some mitigation, but for design, you know, you should, for soil versus rock, of course, you should analyze it for final design, for, you know, numerical modeling and solutions. You have to be creative. These are what I presented is what I understand to be the standard of, or the state of the art of detailing that are kind of details that are proposed today. There may be others, but I'm not aware of them.
Thank you.
I would also have a question. Can I ask? Do you hear me?
Yes.
Yes.
Okay, fine. Look, I'm an Austrian tunneling engineer, and we have a specialty seismic design for Metro Line 7, which is now commencing to be constructed. And the idea was, like we have done in the Polo Tunnel, to separate the tunnel shell in narrow slices to allow for a flexible design in case we get an earthquake shake. The slices can move, and if we provide sufficient oversize of tunnel, the tunnel will remain stable. Only the slices are moved. The railway can be repaired, and the tunnel can be reused. What is your opinion about seismic joints? And which distance between the seismic joints you would recommend?
Well, I do understand your question that sometimes, like for segmented liners, they decrease the length.
Here we have shotcrete lining.
Oh, it's a shotcrete lining.
And the idea was we make a continuous shotcrete lining, and then we cut the shotcrete lining in slices of about 6 to 8 meters.
Yeah.
And with an oversized tunnel, in case the slices are moving then between each other, the tunnel still can be operated. Only the railway must be repaired. The rails must be repaired.
Yeah. I remember hearing about that, and I think one thing is if you have concern for water, and if you need to keep the joints tight. So in the example that I showed for the outlet works, we had overlapping like a HDP joint that would allow, like a flap joint.
Exactly, and then when there comes the tension, the waterproof membrane is flexible and it can go in the direction of the movement, and it will not fail.
The Japanese call that, for the big tunnels, they call that the omega joint, which I think was used on Tokyo Bay.
Omega joint, and in Polo Tunnel, también we have used it, yes. We also used it there.
Yeah, I did not present the omega joint. I think it is in the Federal Highway Manual though, but yeah.
Mm-hmm. And which distance of the seismic joints you would recommend? Our tunnel is a 10-meter diameter, and we have about 2 diameters of overburden.
I think you need to do modeling to find out what's best for your particular ground interaction and liner stiffness.
Okay, but do you have maybe some a geometrical relationship between tunnel diameter and distance of seismic joints?
Yeah, I don't have one rule of thumb off the top of my head. Do you have a rule of thumb?
My rule of thumb is more or less the seismic joint should never be larger than the tunnel diameter.
Oh, that makes sense. Yeah.
More or less clear. We have to calculate all these things, but this is only as first approach.
Yeah.
Okay, and which deformation tolerance you would recommend? Is the second question.
The deformation of what?
The deformation tolerance, or let's say oversizing of the tunnel in case of seismic movements.
Well, that is a combination of the amount of movement you expect and the use of the tunnel. And
in relationship, the distance of the seismic joints. The more seismic joints you have, the smaller the oversizing could be, because the tunnel is flexible and is then moving where is needed. So I thought maybe 30 centimeters of oversizing between the slices.
But yours is a large diameter road tunnel.
It's about 10-meter diameter.
10-meter diameter, and then
a metro tunnel.
It's 10-meter diameter road tunnel.
And 2 railway tracks.
And 2 lanes.
2 lanes of railway tracks.
2 lanes, and I guess and what amount of movement do you expect? 30 centimeters.
From 10 to 15. From 10 to 50 centimeters, maybe.
Makes sense. Yeah, 30 centimeters makes sense.
Okay.
For that project, it makes sense. Not for all
that project. And it's embedded in stiff gravel of Santiago. I don't know if you know this gravel.
Gracias, Michael.
Okay, thank you very much.
Thank you.
¿Más consultas? ¿Una más? ¿Aquí alguna consulta en la sala?
Thank you for the presentation.
Hay una consulta en el chat, profesor.
Ya, tenemos una acá primero, Karina, por favor.
You show a few images where the concrete failed due to the, I guess, compression of the tunnel. But my question is that it failed because the displacement was too big, or it failed because the concrete was not.
In this case, for the Japanese tunnels, I think it's because it's not well designed. In the case of the Bolu tunnel, I'm sure the shotcrete, it was because the it exceeded the magnitude of the strains exceeded the strength of the shotcrete, because that surely was by modern methods, NATM with shotcrete and rock bolts. It wasn't completed. It was initial support, but
you didn't have like the first and second code. The first and second.
It was only this tunnel, these two tunnels, and it was just initial support. And that was probably, it wasn't the materials or improper construction. It's just the material failed because the stresses were exceeded. Yeah. And
Sorry. The same line, there are codes where you can see, like, give you some guidance to science.
yeah, you know, it's a very simple tool is ring compression theory. And you can just look at, you know, the elastic limit of, you know, and when the concrete will fail, and, you know, from the seismic load. And you can also look at the movement the rotation you get with CAD or other tools, just geometry, if you're good at geometry, to figure out how much rotation you have. And as I said, you could use the spalling behavior theory to estimate whether you're in your past your elastic limit of your concrete.
I was thinking more like when you do a building, you have the ACI code. They give some very specific units, but it's like it's very the main idea of the code is for buildings. I don't know if there's the same thing for a tunnel.
Yes, they use the ACI either 318 or 350 for the code, and they have specific guidelines for segmented liners now. The ACI has a guideline, I guess, maybe. And they use the same loading factors and all that. It didn't used to be that way, but I think in the last 30 years, probably, it's 25 years maybe.
I suppose.
Yeah. Yeah.
Gracias. We have the last question. Karina, ¿nos puedes hacer la pregunta, por favor? No estamos viendo el chat acá.
Ya, la pregunta del chat dice, ¿qué alternativas de solución podríamos tener en sobreexcavaciones de gran dimensión que pueden producirse en la ejecución de túneles?
The question is about the solution for excavation. What do you say sobre excavación? For over excavation. The solution.
Over excavation.
It's a general question.
Not to do with seismic or to do with seismic.
In seismic condition,
Maybe
I think.
and rephrase the question.
Karina, ¿puedes leer la pregunta nuevamente?
Over excavation.
But maybe the person can talk.
Sí,
Sí,
quizás eso es más fácil. Eric,
Sí.
yo que hizo la pregunta, quizás la puede explicar.
Well, the mitigation for over excavation in a conventional tunnel would be, you know, fill it with concrete. But mitigation for, you know, a machine tunnel where you're not supposed to have over excavation is sinkholes, and that is also bad news, but you have to fill it with concrete or soil, CSM or something.
Thank you. Bueno, si la persona que hizo la pregunta me la puede hacer después por correo electrónico con más detalle y la respondemos con John.
I have a technical question. Are there more questions? I have one question regarding budget. What percentage of project represents the site characterization of a tunnel? In your experience,
What
in terms of percentage,
what percentage of the project?
is invested in geotechnical site characterization?
Oh, it can really vary, but the minimum is, they say 3%.
3%, right?
Minimum.
Minimum.
Yeah, but some, with all the project delivery methods changing, it can vary between design, bid, build, PPP. What's the other kind? Where you design it and then they could, then a progressive design build. So it can vary. In the United States, they're pushing for the program to spend all the money right away on geotechnical and have very few unknowns because the owner owns the ground. But in other countries, we're trying to convince them that that's the way to go. But in the Middle East and Southeast Asia, they continue to do
Very legal.
a certain amount, maybe 30%, and then the contractor's responsible for the rest. And they can lose lots of money.
So I have a question. So for instance, how many meters are you deploying excavation pits to do the exploration every
maybe for a subway, maybe I want to say 600 feet. Is that 200?
200 meters.
Yeah. But then sometimes they go phase 1, phase 2, phase 3. I just answered an email regarding this, a detailed explanation. And there's a US National Committee on Tunnels and Tunneling 1984 publication. Do you have that? Okay, I can.
Oh, yeah, I have it.
Okay, you have it. So there's that, but then there's also, because of all these different project delivery methods, there's a lot of people doing research on that very question that you're asking. In fact, the California Department of Water Resources is working on that problem right now for a 40-mile-long tunnel. They don't know how much to do.
Are you working, in your experience, it's being more effective, the pressure meter to address earth pressure issues, or
for soil, I know, or what?
or plate load test?
I've used the rock, I'm a rock mechanics, but I use a rock dilatometer, and the pressure meter we've used before, but we did not use the plate.
Okay, so many of the concepts that you were addressing here are mainly focused on rocks.
No, not necessarily weak rock, but we have used the pressure meter for weak rock on the 7.5 mile, 18-foot diameter outfall tunnel. They use a pressure meter. Yeah. So what we do to determine the various moduluses at various strain levels, we do all the type of tests for the various, because you need it for earthquake and you need it for static, and and then we compile, and then depending on the application and the range, then we usually choose the most conservative for that application, like dam foundation loading, or for dynamic, the appropriate curve from laboratory tests or empirical relationships from IDRIS or something.
If you have a comment on that, it depends how much you spend. It depends on what type of tunnel we have. Because now, if there are two projects beyond this, where there's
that's true. Yeah.
Soil conditions.
So mountain tunnels, in fact, the U.S. National Committee specifically addresses the percentage being less for mountain tunnels and rely on geologic mapping and that sort of thing. Because you have the advantage. And you're right, subway tunnels, because there's always something they phase at one, sometimes phase 1, phase 2, phase 3, and sometimes even phase 4.
Certainty is too high.
Yeah.
It's too high. Take risk up to not doing a detailed site characterization.
Yeah.
Very risky.
That 1984 study probably needs to be updated, based on, because I worked on that, the surveys, there the BART tunnels. I mean, I didn't work on BART, but I worked on the survey for it. And it hasn't really taken into the modern tunneling techniques today. And it only went up to like 1980, maybe. No. Yeah, not 1980 cases, maybe. Yeah. So there's a generation of tunneling that would be a good project to update that. It's a lot of work. We had graphs on the wall the size like this. Before computers, we were tabulating all the information.
That was
Yeah.
Bueno, gracias, John.
Thank you very much.
Esta charla ha sido organizada por el Diploma de Postítulo de Túneles y Espacios Subterráneos, la 4ª edición que vamos a realizar este año, que comienza el próximo martes 16 de mayo. Así que, como comentaba, Karina va a compartir mi correo. Pueden hacer preguntas de la charla de Jon y también preguntas acerca del diploma. Y bueno, una vez más, thank you.
Thank you very much.
Gracias a todos. Tenemos un café ahora afuera, están todos invitados.